So first of all, hi everyone. So first of all, I want to thank Christina and Battery 2030 Plus to welcome me here. And I also want to really do a big shout out to Christina for this amazing job that you're doing currently in the European Union for holding everybody on battery and high throughput and computation and experiments together to actually generate more. And I think this is just fabulous. So thank you so much for doing such an amazing job here. Now, this is the title of my talk. I will talk about lithium interfaces in action, designing and fast-track next solid-state battery materials. So the underlying motivation for a lot of my laboratory is really to think a little bit more about climate change. When you think about the carbon dioxide global emissions, then you have about 25% that just stem from transportation and also from making new materials and bringing atoms into new structures. And there is a certain carbon dioxide footprint price tag to do that. Now, when we think about batteries, then I think what is the really great thing about batteries is that you have an opportunity here to really reduce strongly a carbon dioxide footprint by just turning into electric vehicles away from combustion. And with solid state batteries in particular, we have also an option to increase the energy density by enabling lithium in the structures to gain actually much higher values by almost like 30% and actually having much higher capacities. One of the challenges still is, what elements are we going to pick? How is everything that we assemble to new structures halfway carbon dioxide footprint friendly, and what can we do better as chemists to do so? And I think we're all very well aware about, strategies on reducing certain non-so-sustainable or socioeconomically critical elements like cobalt and nickel and others. And these are just all some of my thoughts when I just think about where the world is going and what we should kind of like work more on. Now, what will I talk today about? So I will talk about solid-state batteries, and I will talk in the first part about how to make those very thin and make actually new classes of synthesis and processing within that are having obviously a lower carbon dioxide footprint. And then in the second part, I will talk a little bit more about how to do high throughput synthesis, but not of powders, really of solid-state components that we put into batteries, and some work we recently did here. So what is a solid-state battery? When you consider a classic lithium-ion battery, like in this phone, then you have actually a set of an electrochemical cell where you have two electrodes, cathode and anode. In the middle, you have kind of like a polymer separator and some organic kind of like liquids that are the effective electrolyte of the cell. Because of that setup, you're bound to certain materials, like for instance, taking graphite for the anode, which gives you originally a value for how much lithium can you store in the graphite material for the anode, which is somewhere capped around 370 milliamps hour per gram. Now, the really beautiful thing about a solid-state battery is that you replace this original polymer separator that we just had with a ceramic material. So it's a ceramic that is kind of like stuffed with lithium. The lithium is encapsulated. And by having the ceramic material class as the electrolyte, you enable the use of pure lithium, which has a factor of 10 higher capacity compared to the graphite. And you can choose on the cathode side, for instance, to take actually a full cathode particle material, but also can be still a bit of a liquid, which would be then an almost solid state. So there's different flavors of these batteries. But in a nutshell, in my personal view, solid-state batteries are fantastic. And we can see that in the graph here of energy density over time, of how they develop over the years, because only by the switch of taking a solid-state ceramic electrolyte, you can come to a 30% increased energy density. So we have to turn to other materials to make this jump. And I wish to illustrate that real quick in the graph. So when you look in conventional lithium-ion battery, which is bound to a certain set of materials because of the polymer electrolyte, you can come to about like $120 per kilowatt hour, and you're bound to about 750 watt hour per liter. But this is not over the next decade going to become much lower in price, maybe 5%. But also the energy density is not just magically going to jump 10%. So you're kind of like bound by the original material choice of where you're getting, and you're just optimizing the processing a bit in the fabs. Now, in a solid-state battery, you can get the much higher energy density, which is more like 1,100 watt hour per liter. And that is enabled by the other choice of material. And if you would very critically look at the field, then it's a little bit like where lithium-ion batteries have been like 20 years ago. So the price is much higher yet. It's around $400 to $500 per kilowatt hour. But the projections are that this is going down. And I think there's significant perspective because of the growing market to actually match later on very close to the lithium-ion battery. And it has to, because it will be the direct competitor. So we as chemists and material scientists have to find good ways on how to reduce the synthesis cost to later make it in the race that really solid-state batteries with higher energy densities can realistically enter the market. I want to lose some words about the carbon dioxide footprint. And here's really good news. So if you consider an electric vehicle to the right side and you consider to the left side a combustion engine, then you can see that actually the electric vehicle has about a 60% lower carbon dioxide emission footprint in grams per kilometer on a range of about 150,000 kilometers, let's say a lifetime of a car. So this is really cool news. So even the dirtiest battery, like the really dirtiest battery you can find, you put in, is actually a great battery. And there is no argument for me, and I'm happy to debate it with somebody is rejecting those facts, that batteries are definitely the better way to go for our transportation. Now, there's sometimes people who like to debate and turn around facts. And one fact that is often turned to is to say, well, but up to the break-even point of 28,000 kilometers, well, the combustion engine initially in the production of the car, right? So this car would have an initially kind of like lower carbon dioxide footprint, but not on the full life range. And that shows us something important as scientists. It means that if we produce, for instance, batteries for cars, it's making 30% for the electric vehicle of the total carbon dioxide footprint. So there's still a lot of room to look for synthesis routes that are much better appropriated to have lower carbon dioxide footprints. And I would wish that actually much more work is done in this direction. It's still, I think, known by the companies, but still a little bit ignored by the scientists yet. But it's probably coming more and more. Overall, I think we can say and conclude that it's actually a quite good technologies to enter in electric vehicles. So where's the market right now? And that's showing roughly where the solid-state ceramic electrolyte materials are and the battery manufacturers. So there's on the one hand really companies that are very much involved in making, for instance, solid-state battery electrolytes. There's NGK, there's Corning, there's several others that are around in the market. And then there's others that are considering making full solid-state batteries like ion storage system or Qkera or several others. Also, there is some companies that make hybrids. So it's almost solid-state batteries where you still have the full lithium, which is great with the solid-state battery electrolyte. But then on the cathode side, you use a little bit of liquids with the cathode to just have a fast diffusion. So it's kind of like a diffusion optimized solid-state battery. And there's also several companies like QuantumScape, Cuttle, and some others that are kind of like looking more into this version. And here's, I think, what our tasks are when we consider actually those technologies. So first of all, I think we have to consider in Europe very much that we're not currently so strong in having companies in any of these businesses. And that's a little bit something that we can work a bit on, because if we just look on the flags that I list here, it's very US and Asian dominated. And so we would wish for a good supply chain security in Europe to really see many more company founding to enable actually a good supply chain safety net, that we have actually own productions of materials, for instance, that we need for the solid-state battery tech. And overall, I will also leave that here as a note and pick it up later. We have to reduce the price of solid-state electrolytes very close to those where you find today's cell guard and polymer electrolytes, which is around $1.8 per square meter, just to be very close in where we are living up to. Okay, with that note, I would like to kind of like show you the outline of the talk. I will first talk about how to make thin, slim, and lower carbon dioxide footprint solid-state electrolytes. And I will introduce actually by what is possible currently on solid-state thin film making, how we invented a new low temperature geared method to make actually carbon dioxide friendly, very low temperature produced, stable solid-state electrolyte. And then I will give a note about a recent announcement where I founded a company to produce actually those materials in the way. And in the second part, I will go all high throughput and all fast manufacturing and just show some innovations that we have on how we think we can accelerate material optimization and discovery in the solid state electrolyte space. Okay, so just in general, when you analyze the field, and we have done that some years ago, then in solid state batteries, the classic processing that you find that is most applicable right now for any product is actually in the oxide lithium space to have ceramic tapes that you press out of powders. And in the laboratories, and that's a bit unfortunate, I would say 90% of the research is mostly on pellets. However, you can never really introduce them in a full battery concept later in a car. So it will always be tapes. And there has been some rough projections in numbers where we can see that currently, if you want to make a tape, if you just take the analogous of some calculations known from other tape ceramic making, you have to end up somewhere at about $4 per square meter to be quite close to the polymer separator, which is currently now already at about $1.8 per square meter. So currently the tape production is quite expensive and it's quite challenging to do so. And the main reason for this is that 75% of the costs that you have are really related to the processing. So it's not so much the raw material, it's really all the processing costs that you have. So any way that you find to reduce the temperature and the pressure, or however you make the ceramics, is really great, not only in the costs, but later also by being lower energy, actually, and having lower carbon dioxide footprint in the making. Now, one could argue, well, actually, one doesn't need a tape, right? So the ideal case for the battery would be to have a thin film, right? A very thin unit for the electrolyte that give a lot of volume for the electrodes. And that's something we have also looked a bit. And you can see here the major lithium solid state electrolytes as their categories. So there's the LiPon, LATP, lithium non-atom titanate, perovskite, and lithium garnet. And what's surprising is how long our field needs to recognize and get actually a pellet, for instance, in a laboratory that can't be transferred to industry into the right performance spec of conductivity and electrochemical stability window, and then to make a film structure out of it, just make it thinner. And the answer to all of it is that it takes the whole field, all the scientists, all the engineers in the world, 10 to 15 years just to get something from the pellet processing to the thin film in the right lithiation level and the right conductivity. And we can see that here in several examples for almost all the chemistries except for LiPon. And the reason is, why does it take actually so long to make a pellet chemistry, for instance, as a ceramic electrolyte into a thin film chemistry? And here's why. So we live from structures that are beautiful conductors because they have enough lithium in them to just phase stabilize a structure that is normally not very stable. And that's why the lithium can actually diffuse later very well into hopping of defects in these materials. And the way to do that is normally in traditional powder processing that you over-lithiate a powder. So you kind of like offer much more lithium than it needs, so that when you go into high temperature processing and sintering, there's still enough lithium there to keep the phase in check that is the high conductive one. That's what you do with lithium garnets or perovskites or many other materials. The problem is that lithium is a very volatile material, so you lose it very easily, and the likelihood to lose this is quite high. So there has been all kinds of tricks developed to bring it into a powder that you control, and then later to densify it in sintering to get a tape or pellet. Now, turning to thin films, this is really tricky, because if you were to take a very over-lithiated pellet of lithium garnet, for instance, a good conductor, and you would take, for instance, an ablation technique like pulse laser deposition, which is just a laser shooting on the ceramic target. When the material comes down, you form film. Then you lose, because of the high energy, most of the lithium on the way, and you get very under-lithiated films. And it was, I think, only up to our paper where we could show how to circumvent with a trick the lithium loss problem. So you have to think much more about lithium loss in a smart way. And so here's an idea that we came up with. So we could make the lithium garnet pellet, and you can over-lithiate it only to a certain extent so that it remains dense in sintering. And then we introduced a second target that we made, which is lithium nitride, which is very close to the laser energy and the wavelengths at which we ablate actually with our lasers and material. And if you ablate subsequential, like a multi-layer from both compounds, you can use the lithium nitride as an internal lithiation source by later annealing a little bits of film at about 650 degrees C. Then the lithium nitride decomposes, the nitrogen goes out, And the lithium gets stuck in the lithium garnet structure. And then you get a very over-lithiated, very finely lithium stoichiometry controlled material. And I'm happy to say that this method, meanwhile, that we patented as well, has been applied to several other labs and has led, like we showed in this key experiment, to quite good conducting films. This is how it looks. So you applied kind of like this multi-layer of lithium nitride and lithium garnet. So lithium nitride is only there to serve as the internalization source. And you can see here by the cross-section and the change in the contrast that every 30 nanometers, you get another phase. And when you post anneal it at 650, you decompose the lithium nitride and you have one contrast, because then you turn in the lithium garnet. And this is what we can see in the Raman spectra. Raman spectra are great. They look at the molecular vibration that you excite. And it tells you, for instance, a lot also on the lithium-oxygen bond. So that's why we like it to study actually phase evolution. And if you look at around 650 degrees Celsius, we get towards a reference, which is the cubic fast conducting phase in the lithium garnet, the exact same phase, but now in a thin film. So we have changed the field by offering something that could only be made before in about 100 micron or plus thickness at 1050 degrees Celsius sintering temperature. And we made it as half a micron with 650 degrees Celsius. So we just halved kind of like the annealing conditions by the other processing, and we substantially decreased the thickness by a factor of 100. Now, what's the impact of that? Well, if you study now in an Arrhenius diagram, the conductivity evolution of those films towards a non-lithiated, towards a traditionally lithiated film. So that's, let's say, not this extra route with our multi-layers and then decomposing lithium nitride, gaining a very highly over-lithiated film, then you can see we always end up in the lithium loss phase. And if you choose our route, we end up actually in the high conductive lithium garnet phase. And that's why at the time we were able then to get one of the highest conductivity in a thin film structure for the material. So here's actually what the impact of it was. So you can see here the conductivity at room temperature versus the synthesis temperature. So it's all measured at room temperature, non-conductivity values here. And you can see that the traditional pellets and tapes need these very high temperatures. So we really brought it down here to about like half of the temperature. And in conductivity, it is quite close, within 1 order of magnitude where you would be with the pellets and tapes. And it also kind of like bypassed us very close to the material LiPo at the time, having now another opportunity to make lithium garnet as thin films. So this is all quite beautiful and it's academically quite nice, but it's not really helping the world, what I show you here. And this is why. So what I liked about it is we demonstrated that there is a concept that you can actually have the option to make lithium garnet films as nanostructured chemistries that hasn't been done before as successful. However, the method we choose is like far too expensive. So it's a vacuum chamber. You can't really area upscale it. It's very expensive in doing it. So it's good academically, but it's not really good for really introducing that into other systems. So this is how we thought about how we make dirt cheap storage out of that. And we invented a method which is called sequential deposition synthesis. And here's why I'm gearing up to that. So I love this plot because it shows you a little bit of a reality check. So this is the electrolyte thickness for solid state battery electrolyte. And that's the manufacturable electrolyte area for any battery design. So if you think about the phone that I have here in my hand, so this is about 3 by 5 square centimeter of a battery cell. In a car, you need about 30 by 10 square centimeter of a crack-free ceramic if you want to make a solid-state battery that's really upscaled to this area. And that's actually not so easy to do. So the current cell guard separators are wonderful polymer materials because you can work with them over the whole range of areas. Yeah, so they're very easily area upscalable. And they have a quite low thickness, which is around 10 microns. In classic ceramic production, if you look over the last 50 years, alumina, it took them about 40 years to get a 20 by 20 square centimeter crack-free tape. Yeah, and that's the effort of industry. Currently, I would say that the lithium garnet electrolytes that I know of have been upscaled as tapes to about 5 by 5 square centimeter by manufacturers, or are currently kind of like in designs of that. But then still going from here to here will be fine, but going to the kind of like full battery integration is still some way. There are some companies like a very known Californian manufacturer that I won't name now, that, for instance, look more into vacuum techniques, right? And atomic layer deposition is definitely a very hot one here. And that's similar like what I showed you before in pulse laser deposition. So you're capable to make very thin films, so that's great. But then the upscaling gets very expensive. And it's also hard to do because you're vacuum bound. So reaching 30 by 10 square centimeter, like 12 by 4 inches square is actually quite challenging to do. So here's what we came up with in collaboration with Samsung. So we invented the method called ceramic sequential deposition synthesis. And the idea is here to have literally a spray gun where we offer all the metal salts of the lithium garnet as cations, as a salt, and we bring them in a high boiling point organic. And then we just bring them to a spray gun, we bring it down, we let it rain, and we create a mist where when the droplets hit a heated substrate, they can undergo a pyrolytic decomposition and they can form the metal oxides. This is what you can read in a ceramic textbook. This is now next what you can't read in a ceramic textbook, what was new and saved by the patents and also is published in the paper. So what's very cool is that you can use the ability of many of the lithium oxide phases that you say, well, we can first form a lithium non-lithiated kind of like lanthanum zirconate porochlor phase by just having this at a low temperature, first kind of like reaction, but having the lithium salts still undecomposed in it. And then when you heat it up a little bit more to 500, 600, we can melt actually the lithium salts that is still in it. The lithium diffuses in the structure, and then you have a second kind of like transfer of how the phases are forming. Why this is smart is that you have to control the drying when you come from a direct wet to a direct solid state reaction, and if you don't start from powders. So we avoid the need to have powders being shipped to our lab or any entity and just come directly from the precursors and directly transform that into the right metal oxides. And this is a quite cool method because it allows you actually to go later much more easy in area upscaling. It's very cheap and it doesn't need any fancy vacuum. And in principle, we demonstrate the case in the paper published for a certain set of lithium and other cations salts that we transfer into the lithium garnet oxide structure. But there's many options that you can adapt towards the synthesis chamber that you have and the environment to actually shift and play around and make a whole array actually of different new chemistries. Now, this is why this is cool from a ceramics perspective. So you can see on the left side the nanostructures, and you can see that it's possible in the top view to make crack-free and dense films, and that's no fancy beauty. It's just like the spray chamber. And you can make films that are between 2 microns and 8 microns in thickness, but they have grains that are just like 5 nanometers thin. And we can demonstrate that we hit the lithium garnet phase at around 650 degrees C. So again, we have, like in our PhD experiment, the post-annealing temperature to hit the high conducting phase, but we're much lower. And in footprint, we use much less energy than in classic sintering. It's much better from the carbon dioxide footprint. And the aspect ratio is also better than sintering because you have these very small 5 nanometer grains that are just over a 2 micron cross section, which is almost not achievable with classic sintering. So the aspect ratio for mechanics later as a battery electrolyte is great. Now, we've done some tests with Samsung, and one of the challenge was to take an almost solid state battery setup. So we have a glass fiber and a gel. We have lithium on one side, and we have a reference cell where there's just a normal liquid electrolyte. And then we have actually lithium cobalt oxide, and on the other cell, we spray our lithium garnet electrolyte films in actually at very low temperature and expose that to pure lithium and lithium cobalt oxide. And this is what we can see. So there's actually in the reference cell in red, in yellow, sorry, you see actually that the cell is losing performance. The Samsung cell that was tested in Burlington at around 80 cycles. However, the other cell is going and is actually measurable for a high number of cycles. It's just the very first test, so it's a non-optimized cell, but it demonstrates that you can actually make the films in this way and bring them into cells. We can also see over the C rates that over the C rates, actually, we have a good performance. So we even have like at a 1 C rate and about 80% Coulombic efficiency, which is, I think, quite nice for a cell that has never seen more than 650 degrees C, or in that case, even 500, just made in this way by just bringing in straight electrolytes. So where's that going? So I think that the sequential deposition synthesis that was invented in our work is actually having a large upscale potential. And that's, I think, quite nice. and is actually a very nice way to solve the problem of getting large areas but staying very thin in the thickness, and making actually a new class of processing that could be mass manufacturable for the material. And that brings me to the next thing. So sometimes as an academic, you have to think what is most important, right? And it could be writing a paper, but maybe in some parts it's even not, right? And we have founded very recently, actually last week on Wednesday, we made it official with all the lawyers. We founded the company Qkera. It's Munich-based. And in Qkera, we are now kind of like translating a part of the technology by offering actually small 0.5 micron to 10 micron thick solid-state battery electrolytes that we make actually in a way coming from precursors, and that will enable a wide range of different batteries where we want to integrate that. So the idea is to integrate it in classic solid-state batteries, but also in a part in lithium-ion batteries to enable actually to take a wider range of anodes, for instance, and also as protective layers in some. So that's actually, I think, what's quite nice. We're not a company processing the whole cell. We will be a sub-supplier, but we will be supplying the technology and the materials actually made in this way. And it's a professional team. I'm also proud to say it's a majority diversity-led team, which is quite rare in the battery space. There's CEO and founder LILA Mentorship, who's a very experienced business professional with experience having worked for a very known venture capitalist for several years. Myself and Andy Weiss, who's a fantastic CTO, who are the three main founders, and then also angel founders that are quite known, who went together to make Qkera. Yeah, that brings me to the next part, and that would be actually to talk a bit more about, with all of this knowledge, what can we now do to not make powders, but actually screen for solid state materials. And I want to tell also a little bit on my philosophy on the why. So if I consider, for instance, where the field of batteries is, then there is a big need to actually make fast screening in experiments of solid-state chemistries. And I love this plot. We are about to publish it because it demonstrates that it takes on average, for instance, for lithium garnet chemistries, 15 years to just find the right dopant or the right synthesis route, whether it is hot pressing or different things that people try, just simply to go from the first material has been made for every scientist and engineer in the world to we have the fast conducting lithium garnet that, according to all the DFT data, everything is the best one we can make. And it's really the two things. It's finding the right dopant, so it's a chemical part, and stabilizing the high conducting phase. But then it has also definitely been spending a lot of time on how to make densified solid state materials. In sulfides, it took on average 8 years for solid-state battery electrolytes, and there it's a little bit lower, and I can explain it. I think it is because they have much lower temperature in processing. And so let's say the synthesis itself is, let's say, not so demanding in finding the right temperature pressure scale like in the oxides. On the other hand, those are the ones that have the best electrochemical stability. So this is roughly the price we have. And now I made a calculation. So until my retirement, if we run in the speed with everyone in the field, I could make still 2 more optimized solid-state battery electrolytes until I retire, which would be very boring. So the conclusion from this plot that I once made with my students while still being at MIT in my garden was like, I have to change the way I do chemistry. I'm just too slow. Yeah. So we have to change the way we do things to just get much quicker the materials. And I want to go back here to a paper from Gert, where I think he captures very nicely the idea. So can we do experimentation when we have a fast, high throughput synthesis? We have some proxy characterization, and then we couple that actually in the results interpretation back to decision making, and then actually optimizing the materials themselves using also AI and ML data. And when we think about it, I think in the field, for instance, of biopharmaceuticals, this is used much longer. So just to show you one example of a really good proxy analysis, for instance, in many biopharmaceuticals, you have CH and NO bonds. So it's a little bit different to a battery where you have now suddenly in the chemistries transition metal ions and lithium that's volatile, maybe sodium, right, and oxygen. However, you can use similar analytics, and that's an example where Raman spectroscopy was used to probe, for instance, a very high data set of hundreds of data of, for instance, different bacteria that were present, right, and finding good drugs for that and optimizing that with high throughput. And you can use the spectra like a fingerprint to literally say what type of bacteria it is. So I believe that, for instance, Raman spectroscopy is a great tool to do so for many of the solid state chemistries, because it's especially sensitive to the volatile kind of like low mass elements like lithium and sodium. And also you can capture changes in oxygen vacancies within it, I think, also quite well. So it's particularly well suited to do so in a similar way. And this is kind of like where I see the field going. So there are some people currently working on materials. That's what I'm most interested on, how to tailor those and do some very fast synthesis, but not as a powder, that's boring, but really as a solid state compound, which is much harder. And then there is some probing interfaces and doing fast assembly of the whole battery cells and doing then, you know, also like long-term predictions and performance analytics. So I would love to take it a little bit the notch before, which is really on the material itself. So here's what we came up with. So I just showed you before that we had this invention of the sequential decomposition synthesis. And that's a great method because it directly allows you to go from a precursor into a solid state in a solidified material that you see on the right, but you don't need any classic sintering. And what's beautiful is you don't create just loose powders where, again, whatever you measure has nothing to do after integration in the battery. And I think that this is the way to go. And we're just writing a big review paper about it, if we consider how to quickly kind of like tailor chemistries in the solid state battery space. So to really look for methods that can do a direct transition, maybe not even using particles manufactured. And so we have built a machine, I will show that in a second, where we can do a lot of tailoring of that. And I want to show you real quick one example. This is a Raman spectra of the lithium garnet structure. And if it's high conductive, it's a cubic phase. And there's two features you can use later for probing as proxy definitions. One is it the right phase? For instance, if I make hundreds of those materials at very different conditions, well, then some may be in the cubic phase, some may be in another phase, right? And I want to get the fast conducting one. So I could probe it by just looking at those signatures here in the T2G, A1G, and T2G in the spectra. And if I look, for instance, at the lower wave number bonds, right, the EGs, I can learn a lot about the lithiation level and about the oxygen-lithium-oxygen bonding in it. So there's also this level that I can directly access information. And one can use neural networks and other tricks to kind of like later go over also spectroscopic data and use image recognition, for instance, that can be structure determined or even agnostic to later argue what type of materials was made. Now, as I showed you before, this is a great guinea pig because it took 15 years to find the right dopants and the right lithiation level. So looking now at low temperature, very low carbon dioxide footprint synthesis, we decided to probe the material class and just vary up to 40 samples really as solidified real materials. And we did that in a week. Yeah, you can make in a week 40 different or more samples, not as a powder, but really as a solidified electrolyte. And you could just say, well, vary for me the lithium, aluminum, lanthanum, zirconium in certain extents, and just change temperature and maybe some other parameters in it. And we can directly see how it impacts. So this is how the experiment looks like. So we have created a method with the method sequential decomposition synthesis. We vary the different cations in it. We vary the solvents. And we want them to probe for different annealing protocols, which phases we can access, and just create like a phase diagram of it on the fly, really for solidified films. And this is a little bit on where my student, Jesse Hinricher, who is really in this project, was kind of like analyzing why this is so important. Well, the labor bottleneck, for instance, is often really in the synthesis. It is not so much in later doing the characterization. So you can really say it takes about 1 to 10 hours just to different depositions or any type of ceramic processing. So it makes a lot of sense for us to go here and actually augment here with high throughput and some degree of automation, the processing. This is what we built. So that's, for instance, a sequential decomposition synthesis machine that we built together with the mechanical engineering department at MIT and Professor Matusik's team. And the beauty of it is that we have now not one precursor line like I showed before, but we have many. And we can on the fly mix different cations together. So it's a little bit like when you think about it, you have, some science fiction where you just mix like your elements that you want to have in. And, the theoreticians love doing that in DFT, but we do that here in a real life experiment. So we can just define different precursor lines, there's many attached to it, and just bimingle in the organic different other concentrations of the salt, and then we can deposit actually the films at certain temperatures, conditions, takes them out and then analyze them. And it's, I think, an own construction that we made here, but I think it's quite powerful. So here's one example that I just want to highlight. So we looked into the class of lithium garnet, and I showed you before that what we want to have is the cubic lithium garnet phase, right? So we don't want to have the low conducting tetragonal phase, or we don't want to have the underlithiated or no lithiated pyrochlore phase, because those would be very worse. That's indicating conduction in the lithium conductivity. That's the best. Then there's other parameters that come to play when you process, right? So we want to have nice, dense, smooth films like I showed you before. There's always also some films, if you overshoot temperature, they will look a little bit like the desert, yeah, when you get mud cracks. That's what you don't want to have. It's not a solidified film. But here comes a working hypothesis. If I can make dense films like I showed before, then for the films, I could argue, well, I'm 98% theoretical density. Then I could say, well, then I just study the phase, and I could pre-decide from hundreds of samples which are the ones in composition that I even should object to make a conductivity measurement or object to bring it in a battery cell. And I could do that by studying the Raman spectra, and that's what we're advocating for based on the other arguments, and then have like a decision matrix to say, well, how close is it to be phase pure? And if it's very phase pure and we want to understand the boundaries and write like little atlases, yeah, just mapping out where the boundaries are, how much is acceptable, how much isn't, and how much lithium is in it, and I can map that with Raman, then I can use that as a selectifier to later propose which are the ones that I even want to study conductivity on, because those are the ones that are most reasonable to have a good value. And this would be super helpful because I can measure very quickly Raman data in 5 minutes, and it would help me really to understand the system much better. And that's what we did. So it's showing you one example. So that's, for instance, showing 100 data points taken. And you can do that with an automated Raman. We have here several setups actually that we can use. And you have an incident laser beam that just goes in the sample and rasters, or can raster many samples. And you can say, well, the ideal sample, for instance, for the cubic reference has to look like this. That would be one for the tetragonal and one for the pyrochlore. And we're trying to understand, like for mixed phases, how much is acceptable. And if you're 98% dense, how much will it affect the conductivity? And these boundaries are sometimes not as clear. So over years, this wasn't even published very strongly because people published the best one. But we have now to understand also the bad cases to really propose later where the boundaries are. They will change per material class for sure. And this is now one example where, for instance, we have deposition temperature that we made in sequential deposition synthesis. And we can create these maps where we can show you, for instance, this is what happens in the phase map if you just change the lithiation level. So what's beautiful about it is there is, when you just take the averaged information of the Raman spectra of many, many samples that you have, about like 80 samples, then we can say, well, the samples, for instance, that are created kind of like around like 300 degrees Celsius deposition temperature, had a certain post-annealing that we applied to all of the samples, then we can actually see that there is some that are very close to the cubic reference, that are those, yeah, over here in the very highly red zones. And then there is some that are kind of like showing more tetragonal features, for instance, if you go to very extended lithiation levels, or if you stay very low. There's others, if you stay too low in lithium, and we can clearly see it here where the boundaries are, then we can see that if the nominal lithium is too low, you have, which makes sense, the pyrochlore phase. And what's beautiful about it is it's now a way to have 100 samples that we can make, and we can just tailor through, yeah, the lithium, other cations as you want. And we can use, as we show you here, the Raman spectra to show you where the boundaries are. And where you have even mixed phases, you can't identify it as one or the other phase. And that is what we try currently to understand. And we also go down on a more granular level. And I want to show you that. So for instance, out of the example, we have here an example for the cubic crystalline films, right? So that's the cubic part. Before it was pyrochlore. Over there was more the tetragonal phases. And we can show you, for instance, from several samples and to its references, how the different bonds are actually affected, because it's not that you are static in the phase, but even without a first order phase transformation, you see already small changes in the bond vibrations because of reordering, that we try to understand how significant they actually are later on conduction and phase stability, electrochemical stability at the end on a battery cell level. And this is really terra incognita. These boundaries are actually not known. and we try to map them. So for instance, to give you an example, you can see this is where the lithium oxygen tetragonal and octahedral bond vibrations are in the lithium garnet structure. And we can map now by how much those vary. When you dope, for instance, with tantalum in the system, which is often done to get the high conductive cubic phase, you affect the oxygen, zirconium oxygen stretching bonds quite well, and in turn also the lithium vacancies. So these bonds start to vary much more statistically when we do these tests, whereas the lanthanum oxygen bonds remain always like at the same wave number, very unaffected. So we learn a lot not only about dopants, about phase boundaries, and about, you know, where to kind of like play how much, but we learn also later, can we live in a world where at the future, you make a material, you take one Raman snapshot, and if it's dense, you could just bring in the battery, and you don't even measure conductivity because you have already calibrated that before, that's going to be okay. And that would be a very fast and efficient screening way for industry. I leave you with that thought. I'm very happy to take any questions, and I want to thank, for me, the best team in the world. Thank you guys, you're awesome, and all the colleagues and friends collaborating with us. Thank you very much.
And thank you so much.